Is not on campus today, and so it's my pleasure to introduce our speaker today, Jason Shankel, and he comes to us from Maxis and is one of our core speakers in the series. He's been generous enough to come for several semesters, and I always look forward to his talks because he's a terrific speaker and has a lot of interesting information to pass on. So today's going to be a terrific day. And then just as a little peek into next week is titled on the Colloquium poster as Student Presentations. The first half an hour will be devoted to the 495 students that are working with Dr. Watts on Xbox game development. So they'll be talking about that they've done. And then the second part of that session will be a couple of Dr. Ravi Kumar's students in the data structures class that have been doing some special projects of some type, and they'll be speaking on the second half. I'll get titles out to you and post it around in the next couple days. So for today, though, we get to hear from Jason, and take it away.
Thank you. I'm Jason Shankel. I'm a software engineer at Electronic Arts Maxis. And my talk today is on understanding the mathematics of rotation, and in particular how rotation is used in computer systems that do 3D arithmetic. So, essentially, in any kind of 3D system that you might have, a game or a CAD environment or a movie render or whatever, one of the core operations you have to understand how to perform is how to rotate an object from its definition, which is usually in a local space around its own origin, to an arbitrary coordinate system, which would be like your world space. So, for example, here you might see that we have like the origin is over here in our world, and the hand is oriented with respect to the origin in some way, and the hand will have a rotation applied to it. The hand is usually will be defined with the x, y, and z axes, in its little modeling environment. We want to know what are the coordinates of the hand with respect to this environment. Okay, so in general, rotations can be represented in multiple ways, which we'll go over in a little bit, but the rotation operation, and here are sort of the core principles of it. Rotations represent the orientation of a vector, VR, with respect to an arbitrary origin. Okay, so V0 defines your vector in your local space, and you want to know what VR is in some world space where the vector is flying around and spinning and turning. Okay. Rotations have a multiplicative identity. There is always an identity rotation that preserves R, so that VR times identity equals VR, or V0 times identity equals V0. Rotations have, in part of the identity, also have an inverse. There's always a R to the minus 1, such that R times R to the minus 1 equals I. And you can think of that as a rotation, say about 30 degrees about an axis. The inverse of that would be negative 30 degrees about the same axis, or 30 degrees about the inverted axis. Rotations, most importantly, can be concatenated. They typically define a multiplication operation so that you can have an orientation for the body, say, in this case. There will be some rotation, and then the arm has a rotation that's defined with respect to the body, so that when you multiply the body's rotation times the arm's rotation, you get the arm's rotation with respect to the origin. And then here, the hand would have a rotation with respect to the arm, which has a rotation with respect to the body. And when you multiply those three together, you get the rotation of the hand with respect to the arbitrary coordinate system. And anybody here who's worked with OpenGL will recognize that, I guess OpenGL, this operation of having concatenating orientations is supported directly in the API, where you set up your rotation, you transform all the points that are local to that rotation, you have some other component that's rotating with respect to the thing you're rotating, you push your current matrix, you multiply the top of the stack by the arbitrary rotation, or sorry, by the object's local rotation, and then you get the complete rotation with respect to the origin, then you pop it back off and you push the next one, right? And so this concatenation operation is what allows us to do hierarchical systems and have everybody define their rotations simply with respect to their parent and not have to keep track of where the origin is. And I already have rotation down here, maybe inverted. Okay, so these are kind of the basic operations we expect out of a rotation representation, regardless of what it is. And rotations can be represented, as I'm about to show, in a number of ways. Okay. The three ways that I'm going to discuss today are matrices, Quaternions, and rotors in geometric algebra. Okay, these are the first two are kind of the workhorse practical implementations of rotation, and the third is the sort of boiled down general form of a rotation that's much more flexible and easy to understand, but a little bit harder to implement. I'm going to avoid today talking about Euler angles or arbitrary axis angle rotations. Quaternions constitute an axis angle rotation, so we'll deal with that concept there. And Euler angles are rotations that are defined as a sequence of rotations about the three Cartesian coordinate lines. So you can define a rotation as, if anybody's heard of roll, pitch, and yaw, these operations, storing things that way. Typically, you don't want to use Euler angles to represent your final orientations because they're subject to a lot of problems, especially if you rotate 90 degrees from one axis onto another, then you lose a lot of information because then rotating about x and rotating about z become the same operation, or rotating about x and rotating about y become the same operation. So you can't de-rotate. They're also not unique, they don't animate very well. What they are is they're intuitive. And so we often use Euler angles to construct a little matrix or a little quaternion for an operation like pitching in or rotating about just one axis at a time. But the days of using Euler to kind of represent the total orientation of an object are pretty much long gone. Okay. So let's start with matrices. So a matrix, I'm pretty sure we all recognize from linear algebra. It's a grid of numbers that can be used to multiply by a vector, and the essential general operation of a matrix is to transform a vector of basically arbitrary size, depending on the size of your matrix, from one coordinate space to another. That's what matrix multiplication is, right? And so that's exactly what rotation is. Rotation is the translation of a vector in a linear space from one space to another. Okay, so in 3D operations, we typically work with both 3x3 and 4x4 matrices. A 3x3 matrix stores the rotation of an object, just the rotation and orientation part. A 4x4 matrix stores the rotation and the translation. So out of a matrix, you can get the complete position and orientation of an object. I'm focusing mainly on rotation today, but that's a little important to know. In a 4x4 matrix, the upper left 3x3, a little hard to see, but the upper left 3x3 is the rotation component. The fourth column is the translation. And when you're in a 3D system, the bottom row is always 0, 0, 0, 1, because that's the homogeneous space, and that's used for perspective transforms further down the pipeline. But when you're in a fixed 3D space, you don't worry about the homogeneous components at all. Okay. Now, in a 3D rotation matrix, basically what you have is you have an arbitrary origin, like this, okay? And then you have a matrix that defines three what we call orthonormal basis vectors, describing your translated orientation with respect to your base orientation. So this is your base orientation, and then you're up here pointing off in some other direction, right? You have three vectors that define your new coordinate system with respect to your orbit, okay? And those are the three columns in a 3x3 rotation matrix are the x, y, and z vectors with respect to the origin of the new space that you're rotating into. So when you multiply this 3x3 by a vector, it'll go from being represented in its own local space, like the z vector, to being rotated with respect to the basic origin. Okay? And that's essentially how matrices represent rotations. They are translations of one Cartesian coordinate system to another. Embedded within these components, you can extract the axis and the angle that will give you that when applied to your arbitrary origin, that will give you the new origin. I'm not going to go into all of the arithmetic of that; it's available online. So it's important to recognize that there is a one-to-one correspondence or one-to-two correspondence between new basis vectors for a new coordinate system and a single axis and a single angle that will rotate you there, or a negative axis with a negative angle. So it's 1 to 2 on that mapping. Now, at this point, I want to introduce a concept that's really important when you're representing rotation, is the managing the degrees of freedom that you have in your representation versus the degrees of freedom that you have in your object. And this is an important concept to kind of grasp because it teaches you a lot about the complexity of the representation that you have. Rotation, you might be aware, is a 3-degree of freedom operation, right? So you have rotation about the x-axis, rotation about the y-axis, rotation about the z-axis. And if you've ever heard the term a 6-degree of freedom engine. The 6 degrees of freedom that are being referred to are those 3 for rotation and then 3 for translation, okay? Moving along X, Y, and Z. When you have a rotation system, or a representation of rotation, if it has more than 3 degrees of freedom, you have to apply constraints to it to reduce it down so that your use of it is constrained to only 3 degrees of freedom. And as you can see, a 3x3 rotation matrix has 9 degrees of freedom in it. It's a 9-dimensional entity. Okay, so that means we have to get rid of 6. We have to constrain 6. We have to apply 6 constraints to a 3x3 matrix to make it a valid rotation. You can understand that if you have a matrix and you just plug random numbers into it, you're not likely to get a smooth rotation when you apply to matrix. You get scaling, you get shearing, you get all kinds of activities. So what do we do to make sure that a matrix is a rotation matrix? And the 6 constraints are contained in the name orthonormal. Okay, a 3x3 rotation matrix produces orthonormal basis vectors for a new coordinate system. Ortho meaning right angle, normal meaning unit length. Right? So each of the columns here, what that means is that each of the columns here constitutes a vector that is the cross product of the other 2. Right? So x cross y equals z, y cross z equals x, z cross x equals y. All right. So those are 3 constraints. Each vector is constrained to be perpendicular to the other 2. The other 3 constraints are normalcy. Each vector is constrained to be unit length. Right. So x, y, and z all have magnitude 1. All right. Apply those 3 constraints to your matrix. 9 minus 6 is 3. Sorry, the 6 constraints to your matrix. 9 minus 6 is 3. One more point on the constraining issue. Yes, if you don't. If you do not normalize your vectors, you will get differential scaling along each of the 3 axes that are of different length. So if you have a rotation matrix that's otherwise okay, except for the y-axis is of scale 5, magnitude 5, the others are magnitude 1, then when you go and use it to rotate an object, it will scale by 5 along the y-axis, and the other 2 will be normal. So we often, when we're composing our final 4x4 matrix, we cook scaling into the 3x3 submatrix using just a scaling factor. You just go in and scale each vector individually, or if you have uniform scaling, you can apply it across the board and you'll get your scaling factor. If you do not respect orthogonality, you will get warping and distortion. So if you were like rotating a sphere, instead of it becoming a sphere, it'll be more like a pear or flattened out like a frisbee. You'll either bow it out or you'll pitch it in. We don't typically use that very much for anything inside of ordinary rotation. When we're doing a game or whatever, we want to do distortions or things like that, we apply them as separate effects, but the math is still the same. It's this linear application of a shearing or a squishing force. Okay. So that's pretty much matrices. Now, what are the advantages and disadvantages of using a matrix system? Well, first of all, they're fast in general. I mean, that's the most basic thing. We have today, modern systems have dedicated hardware for vector and matrix operations. You're not going to get any faster way of rotating a vector from one place to another than a matrix. You simply can't. Each component is a product of 3 multiplications and 2 adds, and that's all you could ever hope to get is each basis vector being applied to, so like when you do a matrix multiply, it's x, y, z, and you add them, right? The reason why we have 9 degrees of freedom that we have to deal with is because a matrix is laid out in such a way as to be very, very efficient. So there's lots of redundancy, lots of redundant information in the matrix. And having to apply all those constraints to it is a way that you make sure that the redundancies stay redundant and are not contradictory to each other. Right? And there are also, the generality also allows for scaling and shearing and things like that. And also the matrix operations, once you kind of understand them, they're applicable to things besides rotation. The matrices are used throughout the 3D pipeline to do perspectives and everything else. It's all basically the same arithmetic system. So matrices we can't really operate without them. The main problem with the matrices is that they are difficult to animate. Okay, that essentially what you need to do to animate a matrix is multiply it by an animating matrix. So if I have my head and I'm turning this way, I just kind of need to be multiplying it by some matrix that I've developed with my little axis angle. If I want to interpolate between arbitrary matrices, like I have this is facing this way over here, this is this way over here, and I want to do that, it turns out to be very difficult, and that will see why. So one of the key things we want to do in animation is interpolation. Right? So you can see here I've got my little blue teapot, here's my little green teapot down here, and one is oriented to Z and the other one to X, and I want to generate all of the blue-green teapots in between, right? By a series of, by interpolating from this orientation down to that orientation, getting all the ones in between. Okay? Without respect to representation, the general form of interpolation is this formula right here. Okay? For an arbitrary rotation t from 0 to 1, right? So this is our 0 point for t, this is our 1 point for t. A rotation can be defined as r1, so the blue r here, times r1 to the minus 1 times r2. This phrase raised to the power of t. Okay? So if you go and you do a little plug in here, you plug 0 in, right? You'll see that this grouping raised to 0, like in normal arithmetic, you raise a rotation to 0 and you get identity. Right? This is a ordinary number. Gives us r1. So t at 0 gives us r1, our base value. Okay? When t is 1, right, we see that this becomes r1 times r1 to the minus 1 times r2. And this phrase right here becomes identity. And so r at 1 is r2. And everybody can handle that. t0 and t1, that's fine. What happens when t is 0.75? When t is 0.75, what you have here is a concatenation of two rotations. The inverse of r1 is also a rotation, right? It's just the opposite operation. So this constitutes some rotation raised to the power of an arbitrary value between 0 and 1. Okay. The problem is that calculating r to the t for any given r is very difficult for matrices. To take a matrix and say I want to raise this matrix to the power of something besides an integer is tough. It's defined in terms of logarithms and expressions, exponents for all forms of rotations, and getting the logs and the exponents of an arbitrary matrix, even an orthonormal matrix, is nearly impossible. I wanted to mention, by the way, that the inverse of a matrix is of an orthonormal matrix. If you want to find, if you have r, and you want to find r to the minus 1, it's just the transpose. So you take the columns and you lay them out as the rows. Okay, that's only true in matrix math for orthonormal matrices. It is not the general inverse of a matrix. So when you study linear algebra, you'll see that they have transpose and inverse are two totally different operations. It's very convenient, and so happens for us that in orthonormal matrices, inverse and transpose are the same thing. But don't try to invert an arbitrary matrix by just transposing it. I mentioned that because the log and the exponent functions that you need in order to figure this out talk about the arbitrary inverse of a matrix. But in the matrix formula, what gets inverted in that space is not orthonormal. It's a mid value that is not guaranteed to be orthonormal. Anyway, so when we want to get to interpolation, so that we can do things like sweep our hands through the air like that, we need to move on to Quaternions. I'm going to talk a little bit about Quaternions. So Quaternions, they're pretty much standard usage objects now, but they came into popular usage in 3D about 10 years ago. They generated a lot of confusion. People sort of thought of them as this black art, and you would hear people say things like, "Oh, Quaternions, you can't understand how they work. They're just these weird, magical things that if you just apply this formula, you'll just get the right thing." And like anybody who says that you can't understand something that's defined in mathematics, that's complete bullshit, of course. Quaternions, there's nothing really deeply mysterious about them. You just kind of have to understand what it is that they're doing. So Quaternions were developed by a guy named Hamilton, a mathematician named Hamilton. And what they are is they are four-dimensional hypercomplex numbers. Now, if you remember from high school math, we have I, the imaginary number, is the root of minus 1. I times I minus 1. Right? What Hamilton imagined is a series, these are supposed to be to the power 2. I'm trying to get all that stuff together here properly. Imagine that we have three roots of minus 1, I, j, and k, that share some fairly unique properties. The first is that I, j, and k, each squared, become minus 1. They're all roots of minus 1. Okay. But the difference is that I times j equals negative j times I. And j times k equals negative k times j. And I times k equals negative k times I. So they're anti-commutative with multiplications with respect to each other. Okay. Now the reason that this is interesting for 3D mathematics is that Hamilton basically came up with this scheme, okay, for relating numbers, numerical values, that mimics or maps actually perfectly for our purposes to vector operations. If you think about it from vector mathematics, you have the cross product, right? You have A cross B. The A cross B product is you have an A vector and a B vector, and you basically take your right hand, you sweep across it, and where your thumb is pointing is the direction of the cross product vector, okay? And the magnitude is determined by the angle. Right. So the closer the angle is to 90, the larger the magnitude is. And for two normal vectors, it's 1 when we're at 90, and it gets smaller as we go to 180, which is 0. Okay. But the unique value of the cross product is it's also anti-commutative, so that x cross y is equal to the negative of y cross x. Right. So what Hamilton did here is he basically developed roots of -1 whose multiplication operations mimic the cross product. Okay. And also, when squared, I times I, j times j, k times k, you get -1. Okay. Well, in the dot product for each of the orthonormal basis vectors, x dot x, y dot y, z dot z, the values are 1. So we essentially set the rules for the multiplication and the intermultiplication of I, j, and k follow the rules of vector math in R3. I'm actually not sure why he did that, because I don't think he was too interested in operations in R3 per se. But basically, that is the basis for allowing a quaternion to perform meaningful operations in R3. Its components, when multiplied together, act like orthonormal basis vectors. So forget anything about it you might have heard about, like it's just too weird and mysterious. That's the reason quaternions work. Their numerical components are orthonormal basis vectors. Okay. The fact that the roots of -1 means nothing to us in rotation. It's just basically a convenient axis angle rotation. Okay. So we typically represent a quaternion in the form x, y, z, and w, where x, y, and z are the magnitudes of I, j, and k, and w is a scalar value. So a quaternion consists of I, j values for I, j, k, and w, just like if you ever had x plus I, y in high school, it's the same thing. Okay. So this is a 4-dimensional vector essentially, right? Where you have 3 values for the roots and 1 for the scalar part. Okay. And as we mentioned before, we have 4 values here, and as we know, that's 4 degrees of freedom, and we want 3 degrees of freedom. The one constraint that we apply to quaternions is that rotation quaternions are all normal. That means that the magnitude of these all squared up together is 1. Okay, so quaternion math is a much more general field of study than just rotation, and quaternions are legal all over the place and do all kinds of interesting things, actually. But when you're talking about rotations in R3, we're talking about a subset of quaternions that exist on the unit 4-dimensional sphere. Okay. Now, the significance of the components in a quaternion are that basically it's an axis angle representation. So you use the concept of an axis angle rotation, where you have an object, you send an axis through it, you rotate it about an angle on that axis, right? And matrices are built this way with the components cooked into it. In a quaternion, the axis is the XYZ part, and the angle is the W part is the cosine of the half angle of rotation. The reason that that's important, that's the cosine of the half angle, is it allows a complete sweep from 0 to 180 degrees with unique values all the way through. So from 0 to 1, right? So when it's 1, you're rotating by 180 degrees, right? That's cosine of 90, right? And then theta over 2 times 2 is 180, right? And when that's 1, and you're rotating by 180 degrees, well, there you go. That's 1. Okay. So essentially going backwards, so essentially a quaternion is an axis angle rotation that is constructed in such a way that the normal axis angle rotation doesn't have any constraints on it. The axis can be of any size, the angle can be 10,000 degrees if you want, you know. It's just boiled down to this unique value. What I don't have here, let's see if I move on. Okay. We'll move on to interpolation. The one thing that's important to note is that every rotation is represented by a pair of quaternions. That if you invert each component here, negative x, negative y, negative z, negative w, that's the same rotation as the as the original, because that's 30 degrees around A is the same as negative 30 degrees around negative A. Okay, so this means that really when you have the four-dimensional hypersphere that I'm about to show you, for every quaternion, its inverted mate is the same exact rotation. And this is something that you have to keep track of when you're interpolating, because if you're interpolating between two of them, you might want to check to see if you need to invert to get a little bit closer, to get a shorter trip. So what this allows us to do, this formulation of rotation, allows us to create smooth interpolations using something called spherical linear interpolation, which I'll show you in a second. Much more easier than dealing with a matrix. Okay, so essentially, here's your four-dimensional hypersphere that constitutes all of the quaternions in the world. Here's quaternion A and quaternion B, and all you have to do is plot the arc from A to B and find all the points along that arc, and those points constitute the rotations in between A and B. Now, it's important again to note that if you go the long way around, what you'll get is that you will start in the right place, and you'll end in the right place, and along the way you'll see a lot of spinning. Things will spin its way around. If you go the short way around, it'll go more directly. Also, if you don't pick the right quaternion, say quad A is pretty close to quad B, but you have the negative of quad A, so that you're taking a longer route, say 135 degrees instead of 45 degrees. You'll also notice a lot of spinning. So when you're doing interpolation, you need to check to see if you want to invert one of your quaternions to get it closer, and to make sure that you follow the shortest arc and not the longest arc in order to get a short rotation. If you don't, you get an interesting result. It's really cool. It spins as it goes around, so you might want to do that for fun. What's important to recognize about this is the part where people tend to get generally confused a little bit, is that these values, quad A, quad B, the angle theta between them, okay, which I'll move forward here, let's see. So here's the formula for slurp. Here's your base quaternion, your target quaternion, the angle between them, and as you're moving. And basically that formula I showed you before with the R1 negated times R2 to the power of t plus whatever, boils down to this bad boy in quaternion math. Quaternions define things like being raised to a power of a number and the inverse operation and multiplication, and they're all defined in terms of sines and cosines of the angle between them. Now this is the part that generally tends to confuse a lot of people. This angle that we're talking about between two quaternions has nothing to do with angles or directions or anything like that in your R3 space. Right? It's not the angle between the way you're looking and the way you want to be looking in R3. It's got nothing to do with that. It's just the angle between two four-dimensional objects in this quaternion space. That's the disconnect that a lot of people make. Is like, well, this is these weird four-dimensional vectors that boil back down. And they don't boil back down. It's two totally different things. You're moving things around in a four-dimensional space in order to produce results that, when applied to three-dimensional space, create rotation. Okay. So the angle between two quaternions, which are four-dimensional vectors, right, is given by the dot product, just like it is for three-dimensional vectors or two-dimensional vectors. Dot products, fortunately, are can be defined for an arbitrary number of dimensions because it's just the sumwise. It's just a summation of the component-wise products of each of the components, right? So you basically take a quaternion x, y, z, w. You multiply all the parts together, and that gives you the dot product between them. You take the arc sine of that, and that will give you, or the arc cosines are of that, and that will give you the angle between them. You apply that as the angle that you plug in here for theta in this advanced formula, and for some value of t, that will give you an interpolation. Okay. And that's basically the slurping function that we use to do gentle animations between things. And it can get more complicated than that. You can also, besides just slurping things, you can also create, because you're basically dealing with a sphere. You can think of it as a three-dimensional sphere. You're basically dealing with paths along these spheres, so you can create splines and all kinds of interesting patterns like you would in three dimensions. The fourth dimension doesn't make it much harder to do that. And following those paths will create interesting and graceful series of rotations that will be very difficult to do in matrices. Another way of looking at it also when people started saying, oh, four-dimensional complex numbers, how can you deal with that? The reality is that when you're dealing with matrices, you're dealing with a 9-dimensional number. So what we've actually done is reduce the number of dimensions that are needed. That's why this system works so well. Trying to do this while applying 6 constraints to 9 dimensions, trying to do this while applying one constraint to 4 dimensions is a whole lot easier than it is than trying to apply 6 constraints to 9 dimensions. The last thing I want to mention is when you go to normalize, when you have to apply these constraints to both matrices and quaternions, when you're applying them to a matrix, basically what you need to do is you want to check to make sure that each vector is orthogonal with respect to the other two, and that they're normal, and things like that. And you can get some drift, right? So like you're working with the representation, and you're multiplying along, and it starts to drift a little bit. It's a little bit difficult with the matrix to understand how to put it back so that you will just correct the errors instead of changing the orientation too much. And essentially what you have to do is you extract the axis and the angle, and then you renormalize, then you build a new matrix from that axis and angle that your formula will assure is orthonormal. With quaternions, when you want to normalize, you want to remember that the axis is the part that you typically want to normalize. You want to leave the angle alone. So like say you have a quaternion, you've done a lot of math with it, you've got a lot of floating point drift, and its magnitude is like 0.8 or something like that, and you want to bring it back up to being the right thing. If you normalize x, y, z, and w together the way you sort of just naively just divide by magnitude and call it a day, then you're going to affect w, right? And that's going to cause jitter and rotation as you go along correctly. So instead, what you want to do is preserve w and just recorrect for x, y, and z. Okay, I'm actually way ahead of schedule, so I'll have some questions. The last thing I want to talk about here is the more general approach to solving this problem. And it's actually worth taking a little bit of time on this, I guess. So, with everything I've talked about so far, we're basically talking about systems that exist inside of linear algebra for operating on numbers inside of Cartesian coordinate systems. Okay? That's kind of the core of what we're doing with these systems. And the strength of this is that, well, computers are numerical systems. We're generating numerical results, you know, and we're all very interested in getting numerical values out of everything so that we can show them on the screen and anything like that. So there's nothing that prevents us from using quaternions and matrices for everything that we do. And in fact, that's essentially what we do. The problem is that quaternions and matrices are dependent on this representation, and when you get into more and more exotic and advanced kinds of operations, it's easy to lose your way. They don't easily interoperate. You know, the product of a matrix and a vector is uniquely a vector. You can't work that back out and ask for the matrix part or anything like that. And it's also the case that for most of the operations that we're trying to do in 3D space, they're pretty simple. They're basically just geometric arithmetic, right? We are adding to a translation, we're adding to a rotation, we're moving, you know, we're interpolating between two values. They're very basic operations. However, these same operations are useful in other kinds of spaces. One of them, the most prominent ones is color space. Human beings have tri-valued colors. We see 3 colors and blend them together. Okay, so all of our systems for quantifying color deal with 3 components. You've probably seen this: red, green, and blue, cyan, magenta, and yellow, hue, luminance, and saturation. Okay, we quantify colors as multi-dimensional spaces, sometimes 4-dimensional spaces, usually 3. Okay, so the operations that we want to do, for example, in the color space, are going to be the same kinds of things. They're going to be rotation, reflection, you know, translation, all these things, but they're not going to be as intuitive to us as seeing a ball bouncing down a set of stairs or anything like that. And it's not as easy to just to work in those spaces and just see that you got a good result. You want to be able to understand the geometry of what you're doing. So there's a kind of the new, you know, geometric algebra is the new Quaternions. Quaternions were all mysterious and weird to people 10 years ago, and now they're kind of like, you know, they kind of get what they are. The upcoming mathematics of dealing with rotations and translations is what's called geometric algebra. Now, the value of geometric algebra is that instead of dealing with quantities in terms of number systems, in terms of x, x, y, and z coordinates, they basically just define values. Geometric algebras are also called Clifford algebras. And this is a subject for a huge talk, so I encourage you to go, I'm not going to be able to give you any depth on this today, but I mean, this is the thing to go study. If I'm going to implore you to go study it, it'll be Clifford algebras. And what they do is they define things called cliffs, which are summations of different kinds of components in a geometry. Scalars, which are just magnitudes, vectors, which are directions, bivectors in R2 and above are series of 2 vectors at a time. Trivectors in R3 and above are 3 vectors together. And each of these little components defines a part of a shape. And a cliff is just has a scalar part, a vector part, a bivector part. If you're an R4, if you're an R3, a trivector part. If you're an R4, a 4 vector, a 5 vector, a 6 vector. Geometric algebra, unlike Quaternions, for example, geometric algebra applies to arbitrary dimensionality. You can have a 16-dimensional system, and it'll just, have up to a 16-vector component for defining blades and subspaces. And then they have a series of operations, like if you think of the dot product and the cross product in vector math, right? The operations for the inner products and the outer products in geometric algebra, in fact, dot product and cross product are the inner and outer products in the geometric algebra, produce the kinds of results that you expect from a vector system. Okay, and basically the real strength is that the product of an operation of a cliff with a cliff is another cliff at all times. You are never wandering from matrix to vector to Quaternion. You don't have to worry about how things are represented. You simply say, I've got a cliff, it's got this vector part, this bivector part. It's usually only got one part that's important, but it can be a combination of 2. You can have a bivector with a scalar, you can have a trivector with a vector, and the mathematical operations will work out. So if you get into really hairy and snarly spaces where you're translating from one weird color thing to another, and if you're working with matrices, you find yourself having to invert an arbitrary matrix or construct a matrix out of a vector and a Quaternion because you're in the middle of this whole thing. That doesn't happen with geometric algebra. You're always just dealing with values upon values. And the way to think about it is that we're doing arithmetic with matrices and Quaternions. This is algebra, right? This gives us the general form of arithmetic, the way that algebra gives us the general form of arithmetic. Okay. I'll give you a brief example on this. Rotation, as I mentioned spoke about in matrices and Quaternions, are defined with a matrix. They are defined as a translation from one basis system to another, because you have 3 vectors defining an orthonormal basis. With a Quaternion, the rotation operation is defined as an axis and an angle being applied to a vector. In geometric algebra, what we have instead are things called rotors. And rotors are basically just pairs of vectors, they're like bivectors, okay, that define a rotation. And the operation, the inner product and outer products for vectors can be defined so that a vector can be reflected about another vector. Right? They simply have a reflection operation, the summation of a couple of operations in geometric algebra. So when you want to rotate, say, this green vector to here using this rotor, right? What you do is you simply take the rotor and you apply the reflection operation to the first vector, and you get this intermediate vector, and then you apply the reflection operation to that vector, and it rotates into place. Okay. So at no point are you dealing with any intermediate values that are anything but the things that you're already dealing with. And this allows us in geometric algebra, just as algebra allows us to derive more interesting and elaborate kinds of formulas that you can do with simple arithmetic, geometric algebra allows us to derive more interesting summations of not just rotations, but all kinds of scaling and shearing, and basically anything that you can do in a geometry that you can imagine being done in a geometry can be written out as a formula in this kind of system. So the problem with geometric algebra, and the reason why it hasn't taken over the world, and the reason why you don't see geometric algebra accelerator video cards, is because the representations for geometric algebra are currently very complex. And these operations that I'm talking about, the inner product and the outer product, they're very general, right? And they can apply to pretty much any kind of geometric operations you want to do. And what all that means is that it takes a lot of computer cycles to to calculate a general cliff operation, when in fact you know that you're just doing a dot product or a cross product of a three-dimensional vector. It's a lot easier to just do a dot product or a cross product. Okay? So most implementations of geometric algebra systems have hints and optimizations where you tell them, look, this is a quaternion. You know, this is a vector, and it'll do faster math for you and ignore other parts of it. And there haven't been any systems that have come along yet that have really proven to be much more useful in general as a practical matter for writing code than just going ahead and using a matrix or quaternion. But when you're trying to figure out what to do with your matrices and quaternions, when you want to do the mathematics behind something, being familiar with this it's much easier to derive what you want to do. So typically the way we use geometric algebra is we don't use it as a software system. We don't plug something into a GA accelerator and have it produce a result. We use GAs to figure out what we want to do. We say, okay, I can show you a GA, but this will take us from here, 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 and here, and it'll get us through the red color space while we're doing it. Now let's just go and implement it with matrices and quaternions, because there's a immediate down translation from a simple GA system to matrices. Okay, that's pretty much it for my talk. I have these references here. First is Quaternions and rotation sequences. I highly recommend this for anybody who's interested in 3D development, for physical modeling, or for graphics. This is really focused mainly on physical modeling. It was developed by somebody who was doing a lot of simulations of aircraft and things like that. And it really just gives you a good, very basic rundown of how Quaternions work, how they translate back and forth to matrices, and sort of eliminates a lot of the mystery out of those things. Putting a plug sort of for myself here, Game Programming Gems Volume 1, edited by Mark DeLaura. I have 3 articles in there about quaternions and their interpolation, spline interpolation, and their translations to and from matrices. The matrix and quaternions FAQ has been online for a million years and has a good breakdown. It has all of the formulas that I've kind of glossed over in this relatively short talk. So if you want to see, especially if you want to just look up how to translate, the big operation everyone always wants to know how to do is go from a matrix to a quaternion and back, because you have to do that so much, right? And then for geometric algebra, Leo Dorst, he had a series of papers online. If you Google his name, you'll find them. And he's got a book. I don't know if it's out yet. He's got a site for this, but it's the Geometric Algebra for Computer Science, and he's been the one who's kind of been promoting the development of a practical geometric algebra library. So his site has a downloadable source code and operations for doing GA, 3D, and all that kind of stuff. And that's it. Thank you for your time. I guess we have time for a question or two. Yes?
Are there any games that use Clifford algebra for the 3D currently?
Not that I'm aware of. Clifford algebras are sort of, they kind of came into my consciousness about 4 or 5 years ago. And as I mentioned, probably Dorst has the best Clifford algebra library out there right now. It's pretty fast and it works pretty well. But for the practical reality of just doing rotations in free space and things like that, we usually end up only needing matrices and quaternions. The Clifford algebras, when we use them, it's pretty much to derive what we want to do with a matrix or a quaternion. But the operations that you usually end up with in your derivative formula tend to boil down to matrices and quaternions. So it's like saying, you know, does anybody really use algebra when they go shopping? Well, I can prove to you using algebra that this will cost this and this will cost this, but you basically just add up your bill. So that's kind of the relationship right now. I won't be surprised if Clifford algebras become the new basis for doing a lot of these rotations going forward, because the place where it's critical that we have fast math at this point is at the end point on the cards and things like that. So as long as you can boil everything down to a 4x4 matrix at the end, which everything in Clifford's can be for our group, then you know you'll get most of your speed out. And back when we're doing simulation and multiplying things, it's becoming less and less important for those things to be incredibly fast. And so what you'll probably see is a game that comes out that has very elaborate and impressive, say, animations and color space changes and things like that that would develop quickly. And that'll be probably the first little breakthrough, you know, in the use of Clifford algebras, is that people will just not have to spend as much time developing elaborate keyframe interpolation, spline, quaternion, 4-dimensional hypercomplex systems. They can just say A times B divided by C plus X equals my rotation. Plug that in and get it spit out. The other things that, the other way that we've used Clifford algebra as well is there are systems that will take an expression in Clifford algebras and generate for you final matrix outputs. So you say, here, I want to do this, and it gives it back to you as a sequence of matrices. And we plug those in just as data. But our actual software systems tend to Questions? From us?
What's up at EA these days?
I'm on sabbatical from EA at this point, and I'm in transition. I'm probably going to be leaving EA in the next month or two. We finished up Spore last year. That was kind of the big project that I was, dedicated to being on, and we just finished up the first expansion pack for it. But just speaking for myself, it's a different place than I've been at for a while, and I'm kind of looking to move on. Will Wright left our studio, and he's going on to create this fun club in Berkeley, where they're just going to be making other movies and doing crazy stuff. And so I'm kind of like deciding whether to follow him or look for something else or that kind of thing.
I heard that Will Wright is making making something involving Mr. T.
He wasn't doing that for EA. That's part of the probably part of the Stupid Fun Club. I haven't spoken to Will in about a month right now, so I wouldn't be surprised.
Okay.
Yeah.
Well, we're going to go down to Darwin 28 and have pizza with Jason, our speaker. So if you're interested in joining us, we'll be down there in an informal setting to chat with Jason and games and all. Is that everything for you, Jason?
That's everything.
Okay, so Darwin 28.